Hi, my name is Brian, and I'm going to present you my thesis, Electrochemical Oxidant Generation for Sustainable Drinking Water Purification in Rural Sudoe Areas, a pilot implementation. This thesis was done at University of Castilla-La Mancha. One of the main objectives of this project is water purification, treatment, and reuse, which is done through the implementation of a water treatment train. And one of the stages or wagons of this water treatment train is production process, in which hydrogen peroxide and ozone are mixed together to form highly oxidant hydroxyl radicals. Then the thesis only focused on the in situ electrochemical generation of ozone, and there are two main technologies in which ozone can be generated: coronal discharge or PEM electrolysis. Through coronal discharge, there is a industrial generation, but high use of high voltages and low concentrations are obtained, while for PEM electrolysis, we use an electrochemical cell involving a proton exchange membrane, a PEM, in which water is oxidized to one. Therefore, the core of this thesis is the construction of a pilot-scale 3D printed proton exchange membrane electrolyzer for in situ generation of ozone, in which this is done through several steps. First of all, the design and printing of the electrochemical cell, then validation of the working conditions through several tests involving the optimization of the current collectors, simulations, formation and bubble analysis, mass transfer evaluation, and ozone gas generation rate, which I'm going to talk later, is pretty important, and the pilot implementation through the scale-up of one single cell to 8 cells. So first of all, the 3D printing process of the single-cell electro-ozonizer started with obtaining the case, consisted of two parts, one of each side made with clear resin B40, then obtaining the anode made with niobium coated with BDD, which is boron-doped diamond, then adapting the cathode made with titanium, then the adaptation of the membrane made with perfluorosulfonic acid as the proton exchange membrane, and finally the obtention of the titanium current collectors to provide electrical current and electrical contact to the electrodes through the system and the power supplies. So first, there are also some important features to mention about this 3D printed PEM electro-ozonizer, which was made with stereolithography using the material I just mentioned, clear resin B40. There is also continuous water flow through the system, in which water flows from the bottom to the top, continuously oxidizing to ozone. Also, the use of these hermetic case and rubber gaskets isolates not only the system but also allows the ozone to flow only from the upper side, exiting to the upper compartment. And there is also the use of deflectors and upper outlets pipes that improve the flow of ozone to the upper part. For the second objective, we optimize the current collectors of the system, in which initially they were in contact electrode and current collector to each other, allowing the passivation of the titanium magnetic current collector. So to avoid this, we use a conductive bridge with aluminum and a sealing material, testing several materials and obtaining that the silicon-based sealants show the best performance. As a third objective, we started validating the working conditions, first of all with the computational fluid dynamic simulation using two water inlet flow rates to see how the water performs through the system, and also confirming that increasing the linear velocity increases the bubble movement to the upper part. Then we carried out a gas bubble formation analysis by measuring the distribution and diameter size of the bubbles forming constantly in the system, obtaining that higher water inlet flow rates and higher current intensities allow the formation of macro bubbles, which are better and they are detached rapidly from the liquid to the upper part, forming and transferring ozone to the gas phase. Then we analyze the mass transfer behavior of the system through the use of different water inlet flow rates and obtaining different mass transfer coefficients and by the figure we obtain that increasing water inlet flow rates enhance these mass transfer coefficients and also the improved bubble dynamics through the movement of these bubbles to the top of the liquid. Then we analyze the ozone generation performance through the evaluation of three main variables: water inlet flow rate, temperature, and current intensity, using two levels for each variable, as you can see here in the description. And we started analyzing with the liquid phase. The liquid phase is where the ozone forms initially, and then it transfers to the gas phase. So in the case of this system in which we want to obtain ozone gas and we want this in the gas phase, we don't care about the liquid phase, but we care that we keep it as low as possible. So in the liquid phase, this is where ozone forms and then it moves to the gas phase. So in the case of the ozone generation rate in the gas phase, we obtain at these mentioned conditions the milligrams of ozone formed per minute, in which we obtain that the efficiency is improved when increasing the water inlet flow rate and current intensity, and that the current intensity is the factor that has only the most significant effect. And obtaining and analyzing from these figures, we obtain that the maximum and optimal conditions for ozone generation were at 3 amperes, 540 milliliters per minute, and 5 Celsius degrees, in which we obtain 0.69 milligrams of ozone per minute and 3.53% of efficiency, which compared to other results, we're going to show that they outperform. So the final objective was the construction of the pilot plant prototype. In this case, we had this PEM electro-ozonizer, the single cell, with the improved conditions, improved supports, and also the obtention of the optimal conditions to carry out the scale-up, in which we analyzed and we estimated the required number of cells to obtain 4 milligrams or around 4 milligrams of ozone per minute to be done with 8 cells. This description allows us to see how is the installation be done. And in this case, the solar panel provides electrical supply to all electrical devices, power supplies, the gas analyzer, cooling system, pumps. And as you can see, there are 8 cells connected in parallel, in which there are 2 main stacks. And the ozone is generated from each stack, and they join together to redirect to the gas analyzer to measure how much ozone is being generated per minute, and then it goes directly to the ozone process. Finally, for the installation of the PEM electro-ozonizer at the pilot prototype, we can see in the video that the PEM electro-ozonizers are connected in parallel, not only hydraulic but also the electrical part. Additionally, the gas analyzer needs to be added downstream to analyze the ozone, and also this ozone then needs to perform in the production process and be measured how much it is the efficiency to oxidize and to form hydroxyl radicals in this process. This is out of scope. And then the current progress, as I mentioned, this is a partial implementation, so there are still some elements missing, some devices like solar panels, like also the connection of the cooling system and the addition of the gas analyzer. And it is also undergoing the electrical panel installation and cooling system panels to add controllers and to facilitate the monitoring. Thank you for watching.